All right, so we are in the midst of a pursuit of a good approximatio algorithm for ratio cut. And that involves 3 steps. The first is that we created an LP relaxation for the ratio cut problem, where we have edge lengths dij, which are, edge length yij, which define distances, or what we intend to be distances, dij, with triangle inequality constraints, saying that dij is less than or equal to dik plus ykj. Okay. And we then constrain that the sum of all the distances should be at least 1. The vertices need to be far apart from each other on average. And we want to minimize the volume of uij times yij, right? Minimizing the volume with the constraint that the distances should be, that the sum of distances should be at least 1, is equivalent to minimizing the ratio between the volume and the distances, because you can always this linear program doesn't have any constants in its constraints, and so you can multiply or divide all the variables by whatever you want in order to get the ratio. And we said that this was a relaxation because given the optimum cut S comma t, you simply assign yij equals 1 if ij crosses this cut. Sorry, not 1. 1 over size of S times size of t if ij crosses the cut, right? And this means that any path from the left side of the cut to the right side of the cut has to use one of these cut edges, and so any path from the left side to the right side is going to have length at least 1 over S times t. There are S times t pairs that are split by the cut, so the sum of the distances will be 1 if you use this assignment. At the same time, the sum of the sum here will end up equal to the ratio that we're trying to minimize, right? Because it's just going to be 1 for all the cut edges times the capacity of those cut edges divided by the ratio term in the denominator. So that was the first step of our approximation algorithm. There were 2 steps remaining that are based on recognizing that we have here defined a metric. Because a metric is just a set of distances that satisfy the triangle inequality. Yes? Uij is the capacity of edge ij.
So are we doing like the ratio plus on a weighted graph?
So you can look at this problem on a weighted graph or an unweighted graph. And actually, I wrote down the linear program for the weighted graph. It doesn't really change anything, right? If you have a weighted graph, you can just think of it as many edges that are parallel, and then you're back in the unweighted case. And everything that I'm going to be saying about the approximation works equally for unweighted and weighted graphs.
So in an unweighted graph, you would just have dual pi j equals 1.
Correct. Okay. All right, so we have that this LP defines a metric. It gives a distance between every pair of points, namely the shortest path distance. Right? You can see, right, the fact that we are trying to that we are forcing the sum of the distances to be at least 1, but we are enforcing a triangle inequality, right? So we want the distances to be large, but we're not allowed to make them bigger than the shortest path distances, so they will end up equal to the shortest path distances defined by the Yij's. Okay. So the Dij's will tell us the lengths of the shortest paths, and so that defines a metric on the vertices of the graph. We are going to round that metric. And we're going to do that in 2 steps. The first is we are going to embed our metric into L1 with order log n distortion. Okay. And if you remember the definitions, right, L1 distance from x to y is just equal to the sum over all of the coordinates of the absolute value of the difference between them. So it's the so-called Manhattan metric. And distortion comes from our definition of embeddings, right? So again, an embedding can always be scaled, but we talked about contractions last time, which are embeddings that don't increase any of the distances. And if you don't increase any of the distances, then the distortion is how much do distances shrink at worst, right? So when I'm saying here order log n distortion, I'm saying that every distance in the embedding is at least 1 over log n times the distance in the original metric. And also, I'm going to assume it's a contraction, so every distance is at most 1 times the distance in the metric, right? And that distortion is going to play an important role. I'm then the second step that we take is we show how to round an L1 metric to a cut with approximation ratio 1. Okay. And since we lose nothing in the rounding of the L1 metric, all of the error in our approximation comes from the embedding. Okay? And if we go back and look at our linear program, right, we've just said that we don't make any of the distances bigger, right? Which means that our objective function under the new embedding is not going to get bigger, right? And it's the numerator of the ratio, right? Meanwhile, because it's a contraction, because the distortion is only log n, each of the Dij's is only going to shrink by a log n factor at worst, which means that the sum of the Dij's is still going to exceed 1 over log n, right? So our numerator is getting smaller, our denominator is only shrinking by a log n factor. That means that the ratio in the embedded metric is at worst order log n times the ratio in the original metric. And we then round that with approximation ratio 1, so we get a log n approximation to the ratio cut. Is this clear? Ask if it's not. Okay, so this is the order in which you execute the algorithm, but I'm actually going to present it backwards. I'm going to talk about the rounding first. So I'm going to suppose we have embedded G into L1, G with the given LP solution. Into L1. Okay. What that means is that the dij's will now refer to L1 distances. Okay. You'll notice that if there is an edge, right, dij is at most yij for any edge ij, right? Because you can always use the edge to go between them. There might be a shorter path using a chain of edges. But we can still talk about the, and so we can now talk about the ratio in this embedding, right? Right, where we're looking at certain edges, certain vertices that are at a certain distance in the graph, right? Sorry, hang on a second. Yij. Yeah, actually, dij is going to be equal to yij. Because if dij is bigger than yij, then I can make yij smaller, right, in the LP, and get a better objective function. Okay? Yes? Exactly. Technically, we can forget about the y's and just talk about the d's, right? And so we can talk about the ratio in this embedding, right? In the numerator, we have the sum over edges ij of dij, and in the denominator, we just have the sum of over all pairs of dij, right? Now, I am going to give you a rounding scheme, preserve all the dij's in expectation. So intuitively, this is not formal, but intuitively, the numerator will be equal to its expectation after the rounding. The denominator will be equal to its expectation after the rounding, and therefore our rounded solution will have the same ratio as the metric does. Okay? Now, of course, you know that you can't take expectations of ratios and expect nice things to happen, so we're going to have to be a little bit more careful, but intuitively, that's what's going on. Right, so here's how I'm going to do this embedding. So first of all, I'm going to scale the metric such that it fits inside the unit cube in whatever number of dimensions we are dealing with. It is unfortunate that I'm using D for both distance and dimension, but I'm not going to be talking much about the dimension because the dimension actually doesn't matter in this analysis. It can be whatever it is. Okay? But I'm going to just, if the graph is very big or if it's been embedded somewhere else in space, I'm just going to bring it into the unit cube by scaling it appropriately. Okay. Now, in order to round, all I'm going to do, this is a generalization of the ST min-cut trick that we did. Okay. I'm going to pick a random dimension. And I'm going to pick random cut point in the interval 0, 1. Right? And again, right, we're working in our cube. I am terrible at drawing. So I'm basically going to pick a dimension, maybe it's this dimension, and I'm simply going to draw a hyperplane that cuts through this dimension, that cuts perpendicular to this dimension at whatever distance I've randomly chosen. Does this make sense? So it's essentially do the ST min cut rounding in a randomly chosen dimension. Okay. So now let's ask, what is the probability that vertices x and y get separated when I do this? How do I figure this out? Yeah? Exactly. So let's sort of break that out, right? If I choose dimension I, then the probability that I separate them is just equal to the absolute value of the difference of their coordinates in that dimension, right? So again, if you think of Manhattan, right, either I'm cutting north-south or I'm cutting east-west, right? And if I cut, if my cut is north-south, then what matters is how far apart are they from east to west. If my cut is east-west, then the question is how far apart are they from north to south, right? You could probably make a great movie out of this with these giant force fields, you know, the aliens dropping these giant force fields down that cut pieces of Manhattan off. And, oh my God, 3rd Street's been separated from 17th Street. Okay, but we are choosing a dimension uniformly at random, right? So the overall probability that we get cut is just 1 over the total number of dimensions times the sum of the difference in that dimension, right? But what's that sum? Yeah, that's the L1 norm, right? So the hard part is done, right? We have this very simple rounding scheme whose probability of separating two vertices is equal to the distance between those two vertices under the L1 metric, right? Yes, I did turn this on. Okay. It's scaled by this factor, but, you know, so be it. Okay. So this means that I can go right back and formally assert what I asserted before, right? Since the probability that I cut edge ij, or separate the endpoints of edge ij, is just equal to the distance between the endpoints, the expected value of the numerator under this rounding scheme is going to be equal to the value of the numerator. And similarly, the expected value of the denominator under this rounding scheme is going to be equal to the value of the denominator. Right? So now we just have to sort of be a little bit careful since ratios don't always work nicely with expectations, but things work out nicely in this case. So I basically have two random variables to worry about. I'll call one of them x, which is equal to the total value of the cut edges under this rounding scheme. and y, which is equal to the denominator, right, the product of the two sides, which is just equal to the total number of cut pairs of vertices. Okay? And we know that the expected value of x is just equal to sum of uij dij. And we know that the expected value of y is just equal to the sum of the dij's. Yes? So now let me write down a little helper lemma. And I'm going to write it the obvious way, and then take the contrapositive, which is what we need. We also, so let's see, how do I want to state this lemma? If yes, if for all sample points x is less than or equal to beta, let's say, let me just make sure I put it in the right direction. I might have to flip the orientation of the sign, but let's figure it. Let's do that later. And somewhere x is less than beta y, then the expectation of x is less than beta times the expectation of y. Okay. And this is a statement about any two random variables, right? If one of the variables, it's kind of a coupling statement, right? If one of the variables is always less than beta times the other, then is less than or equal to beta times the other, then obviously the expectation of x is less than or equal to beta times the expectation of y, right? I've added in this other condition. This is actually just to handle some pathological cases, but as long as x is strictly less than beta y somewhere, that's going to drag down the expectation of x. And this restriction that x is never bigger than beta y is going to prevent you from canceling out that downward drag, which means that the expectation is going to be strictly less. Okay? And yes, I did get these all backwards. Let's just flip these around. Okay? So this is straightforward. I'm actually going to use the contrapositive. If the expectation of x is less than or equal to beta times the expectation of y, and here beta is the ratio achieved by the LP. Right? So if the expectation of x is less than or equal to beta times the, right, if this is not true, then the antecedent has to be not true, which means that either there exists a point where x is less than beta times y, right? Or else x is less than or equal to beta y everywhere. Everybody agree that's the contrapositive? So let's think about what that means for our particular rounding procedure, right? We have arranged for the expectation of x to be this quantity, And we know that this quantity divided by this quantity is our optimum ratio beta, right? Which means that the expectation of x is equal to beta times the expectation of y, right? And that means that either, right, there exists a point where the value of the cut is less than beta times the number of separated pairs, or else the value of the cut is everywhere less than or equal to beta times the number. Now, why do I have these two conditions in? It's just to deal with this annoying situation that when I do the rounding, there might be some dimensions in which the graph does not reach from 0 to 1, right? Which means that there are going to be certain rounding points where I put the cut through and it cuts nothing, right? So the value of the cut is 0 and the number of separated pairs is 0 and the ratio is 0 divided by 0 and, you know, bad things happen. So, but on the other hand, if we don't do the division, it is certainly true that 0 is less than or equal to beta times 0, but that's not interesting because it's not a cut, right? But if we use this sort of wordier formulation, one of these two things that happens. Either every point that you pick for x is less than or equal to beta times y, and we know that some of the points induce a cut, right? And so if you induce a cut, then you have a valid cut with the appropriate ratio, right? The other possibility is that there's a point where x is strictly less than beta times y, but that means that y isn't 0, right? And so that means that that also means that you have a cut. So whichever of these conditions hold, you have a cut. And its ratio is at most beta times the value of the cut is at most beta times the total number of separated pairs. So this achieves a cut with the desired ratio. Is that clear? There's probably a more elegant way to avoid talking about these two cases, but this was the best I could come up with. So any questions about, and so this is actually sort of an interesting general statement. You can generalize what we've argued here to conclude that essentially every L1 metric is just a convex combination of cut metrics, right? The cut metric is the metric where you separate the points in two, and the distance between points on opposite sides is 1, and the distance between points on the same side is 0, and this trivially satisfies the triangular inequality. It's sort of the most trivial, non-trivial metric, right? And so the L1 metric is just the fractional version of cut metrics. So it's actually a very simple metric structure. Yes?
For the scaling down to the unit cube, isn't it like an issue if we scale everything to be very small? Because then like almost all of the time you try to cut, you don't actually get the value.
So this is an interesting, so what you're saying is, sorry, let me put it another way. What I have done so far is given you a probabilistic method proof that there exists a good cut, right? Now, how do we actually find that cut? And I'm going to argue that we can actually de-randomize this argument. To find the cut. Okay. How can we de-randomize this argument? Well, what we do is we recognize that, you know, in a given dimension, we have all of these points where we might put the slicing plane for that dimension, right? As we sort of scan the plane from one side to the other of that cube, where do things actually change in sort of the outcome of putting, right? If I move the plane a little bit, it's not actually going to change the cut unless something very specific happens. Yes? Exactly, right? The value of the cut induced by the plane only changes when the plane crosses a vertex. So there are only n different values only n different cuts that are defined by the slicing hyperplane in one dimension, right? And I can figure them all out just by looking at the vertices in order, right? The cut puts the first k on the left side, and the second k, and the other n minus k on the right side. So you can just read off the cuts, and actually you can sort of read them off dynamically, right? You start with everything on one side, you start scanning, you take the first vertex, it goes to the other side, and so you know that all of its edges, which were currently on the same side, are now cut edges, right? So all of the edges leaving the first vertex become cut edges, right? When you get to the second vertex, the same thing happens. All of the edges that were still going forward become cut edges. All of the edges that were going backward stop being cut edges. So the update time for moving a vertex across the plane is just proportional to the degree of the vertex, where you subtract and add various edge weights, right? Which means that this entire scan is only going to take you linear time, right? So if I update the cut values dynamically, you have a linear time algorithm for computing those n cut values. You do this in each of the d dimensions, and that's the total runtime of your rounding algorithm. Yes? Yes. So this is what we have to do next. We have to address this question of embedding in L1. Okay? Oh, people are actually evenly spread out today. I was going to offer to reuse these boards instead of making everybody's necks crick, but I'll just keep. Yeah, okay. So if you would like me to not use the far boards, I will recirculate sooner. But I think out of fairness, I'll use this pair of boards. All right. So I'm going to show you this very beautiful embedding due to Bourgain. Bourgain shows that any metric on endpoints can be embedded in L1 using order log n dimensions with order log n distortion. So that's the answer to your question. Yes? Oh, I'm sorry. Yes, log n squared dimensions. But again, the point is that the number of dimensions doesn't really matter here, right? Our rounding scheme works for any number of dimensions. It just means we're going to take m log squared n time in order to do the rounding instead of m log n time. Okay. What really matters is this very small distortion, all things considered. Okay. I will mention that Bourgain is an alive working mathematician. Like it's every once in a while you sit back and think about how young computer science is. That the things that are cutting edge work were developed in our own lifetime, right? I should also mention that last I checked, Chernoff was still alive, right? He's 102, I think, or maybe 103. What was that? With high probability, he is still alive. Yes. Okay. So, and this is true for any metric. So it of course applies to the metric that we define using linear programming. Okay. So, how do we do the embedding? For each power of 2, up to n, we are going to pick some number L, order log n, random subsets of n points. This actually has some shades of the L infinity embedding that we did. Right? Remember that in the L infinity embedding, we had a coordinate for each point, and we set that coordinate equal to the distance from that point. Right? So what we're going to do here is, this is going to give us a collection of sets AI of various, not random subsets of endpoints. Let me say this better. How do I want to say this? Yeah. Of 2 to the I points. Right? For each power, for that many points, whatever the power of 2 is. Right? Yeah?
It's still log n and log I for the number of subsets.
It is log n subsets, but the subsets are of size 2 to the I at different powers. Okay. Actually, I think it's easier if it's n over 2 to the I. Not that it makes a huge difference. Okay. But this means that the probability of a point being in the set is 1 over 2 to the I, which is nice. So we have this collection of sets, A sub I, although this is a different I, of L log n sets. And now for the embedding, I'm going to set the ith coordinate of point U in the embedding to be the distance from U to the set A sub I, which is equal to the minimum over V in that set of the distance from U to V. Okay? So it's like the L infinity embedding, except instead of considering individual points, although, I mean, when 2 to the I is equal to the n, we'll be picking sets of size 1, just like in the L infinity embedding, but we also take some bigger sets and look at the distance to those larger sets. Okay. Then we're going to divide by L log n, which is just a scaling factor to make it a contraction. Right? We can always scale our metric however we like. Right? If we have a certain distortion, if we have certain changes in distance, this just makes those fit into our definition of distortion, right? Which only applies to contractions. Okay. All right. So I'm going to prove to you 2 things. First of all, I'm going to prove to you that this is a contraction. So why is this a contraction? Well, suppose that a particular set, a particular vertex or point inside of AI is the argmin of the distance from U to V. Right. So suppose S is the point that determines the distance of U from set I. Okay. And T does the same for V. Well, then we know that the distance from U to S is less than or equal to the distance from u to t, because s is the closest point to u in this set. But we can certainly add on some more distance without changing this inequality. Whoops. Triangle inequality. Right? Distances satisfy the triangle inequality. But now if we move this around, this tells us that the distance from u to s minus the distance from v to t is less than or equal to the distance from u to v. Right? But this is the distance from u to a, and this is the distance from v to a by the definition of s and t. Right? And remember that this is the ith coordinate of phi of u, and this is the ith coordinate of phi of v. And so I can apply the same argument in both directions and put some absolute values here. Right? But of course, this is the contribution of this coordinate to the L1 distance between u and v. Right? So this implies that the unscaled L1 distance between u and v is at most d of uv times the number of dimensions, which is L log n. So once I scale by L log n, all of my distances will be, none of my distances will be increasing by the embedding. So that proves that we have a contraction. Yes? No questions? Okay. So now that we have a contraction thanks to this scaling, I just need to talk about the distortion. Right? No distances grow, so how much can distances shrink? So we're going to show that essentially what would cause distances to shrink a lot is if we keep on picking sets that bring u and v really close together, right? We're gonna make u and v appear close if the set that we pick has one point that's very close to u and another point that's very close to v, because then the distances between them will, the difference between their distances will be very small, right? Or actually more generally, if we pick a set of points that are all sort of equidistant from u and v, right? So that their distances cancel out from each other. So we have to show that that doesn't happen, that we don't accidentally bring together 2 points that are really far apart. And we're going to show that by demonstrating that thanks to this random construction of sets of different sizes, we are guaranteed, or in expectation, we pick sets that have points close to one of the endpoint, one of u and v, but not to the other. Okay, and so if we have points that are close to one of them and not to the other, then one of them will have a small distance to that set, the other one will have a large distance to that set, and so the distance between them will show large in that coordinate. Okay? So I'm going to define a sequence of important distances. I'm going to let rho t be the minimum radius such that the ball, I'll define that in a second, the ball around u of radius rho t and the ball around v of radius rho t both have at least 2 to the t points. Okay. The ball is just all the points within distance rho t of the center point u. Okay. So we draw a circle of radius rho t around each of our endpoints that we're paying attention to, and we see how many other points are contained in those balls, and we basically grow rho sub t until we get at least 2 to the t points in both balls. Okay. Notice that if rho t is smaller than, say, the distance between the points divided by 3, then the balls are disjoint. Right? Just another application of the triangle inequality. Okay. So I'm going to assume, without loss of generality, that, well, we're growing until both balls have at least 2 to the t points, which means we're going to stop when one of them has exactly 2 to the t points. So without loss of generality, I'm going to call that u, right? B of u rho t has exactly 2 to the t points. Okay? And this defines a whole series of rho t values, of course. Meanwhile, the ball around V at radius rho t minus 1, by definition, has at least 2 to the t minus 1 points, because that's the definition of rho t minus 1. Yes? So we have one ball with at most 2 to the t points, and another ball with at least 2 to the t minus 1 points. And for theoretician purposes, these are basically the same number, right? They're only a factor of 2 apart, right? So the claim is that with constant probability, a sample of n over 2 to the t points contains a point of the smaller ball, but no points from the bigger ball. Whoops, rho t. Okay. So remember, we're taking n over 2 to the t points, right? So in expectation, right, we are taking 1 point from u's ball and half a point from t's ball. So both of these are right around 1. And by now, your intuition should be developed to the point that, if the expectation is 1, it means there's a constant probability of 0 and a constant probability of not 0. Yes? And I can work that out formally if you want me to, but I'm hoping you all just sort of see that as reasonable. Right? And these are disjoint balls, so these are disjoint events. So we don't have to worry about dependence, right? So there independently is a constant probability that I get no points from the rho t ball, and a constant probability that I get points from the rho t minus 1 ball. Okay. And so this assertion is true. Any questions about that? So if that happens, it means that the distance from u to this set that we've chosen, right, is larger than rho t, because we didn't get any points that were close to u. But the distance from v to this set that we've chosen is less than or equal to rho t minus 1 because we did pick a point inside of V's ball. Right? And that means that the difference between their coordinates with respect to this with respect to this set is at least rho t minus rho t minus 1 by the triangle inequality. Right? Or sorry, by the definition of the embedding. Okay. So, in other words, with constant probability, the sets of size n over 2 to the t contribute rho t minus 1 to the embedded distance between u and v. Which means that the expected distance is equal to omega of the sum over all of those different t's of rho t minus 1, which is just equal to, right, we keep growing these balls up until distance duv over 3. So by telescoping, right, at different sizes, we end up in expectation getting a total contribution to the distance of which is equal to the actual distance. Yes? And now we're basically done, right? But remember that we did this L times, right? So we made L sets of each size, right? So the actual distance that we get so the expected total distance is L times that duv over 3. Okay? But now we divide, we had the scaling factor of L log n. So we end up with duv divided by log n. In other words, we have shrunken each distance by only a log n factor. Okay? So notice how L didn't matter for the distortion. It gets canceled out by the scaling. Why do we pick a large L? Yeah?
Because we want this to work with high probability.
Exactly, right? What we've argued here is that we get a good distance in expectation, right? By using a large L, right, with our Chernoff bound, we can say that with high probability, right, whatever this constant is, we can say that with high probability, a constant fraction of the sets that we choose has this right property, right? And that means that we get a tight concentration of every distance around its expectation, right? And therefore, right, we can say that the distance between u and v is correct, right? Low distortion with high probability, and now we apply the union bound to every pair of points in order to, right? And this is why we need to set L equal to log n, right? Our high probability result is, exponential in L, and we need it to be 1 over a polynomial so that we can apply it to all pairs of points in the metric space simultaneously. Okay. So this is Bourgain's embedding. It's beautiful. It's had many, many applications. But this is all we need to say about it for the purposes of our ratio cut. We're now done, right? I've shown you how to take an arbitrary metric and with this very straightforward, very practical algorithm, turn it into an L1 embedding. And then with this really simple rounding scheme, get a cut with the same value. So it's weird. This is a problem which is technically very difficult to think about, right? There needed to be a lot of lead up to it and so on. But the algorithm for it is one of the most trivial we've seen all semester, right? I mean, you solve an LP, you pick some random subsets and compute some distances, and then you sort the points and look at cuts, right? Nothing to it. It's all in the complexity is all in the analysis, which is really my favorite kind of algorithm, because you can implement it in an hour, and you know somebody else did all the work to show that it's correct. Right? Okay, we've hit 4:30. Let's take a break. I'll give some wrapping up remarks about these ratio cuts, and then we'll move on to our next topic.
Oh, I guess we can change that. We had an extra hour a day. Oh, wait, we copy. Please, we're copying them. Well, I'm going to be late for this one again. Well, there's going to be another. Why are you always because I have 5 minutes.
She'd much rather be doing the homework over Thanksgiving than getting it done ahead of time.
Oh, I mean, I don't want to. You can just go home. Well, wait. Are we going to have like a standard?
No. So done with break. Logistics first. Tonight I will hand out the final problem set, which will be due next Wednesday. So you won't have to do any work on Thanksgiving, although, of course, if you want to use all of your Slack points so that you can enjoy Thanksgiving doing problem sets, that is your prerogative. Judging by past experience, almost nobody will be here next Wednesday, and so I'm not going to hold a lecture on Wednesday because it's the day before Thanksgiving and everybody's traveling. Okay, so I never have a decent turnout for the day before Thanksgiving. If a lot of people will be here, I can lecture on something fun and optional, but I don't expect it. On this problem set, the project submission will be required because I want to look at your proposals before Thanksgiving so that there's time for you to pivot if you need to. The optional didn't work very well. I think I have 3 proposals. I'm a little behind on assessing them, but I'll get those assessments back to you quickly in case you need to pivot. Yeah, and that's it. After Thanksgiving, you'll just work on your projects. There is a required class attendance on the last Monday, 2 days before the last day, for a peer editing session, which is very important because papers get much better after your classmates look at them and tell you they can't understand them. And that's much better than me looking at them and telling you I can't understand them because my opinion comes with a grade. And then we won't have class on the last day, although I might do a focus group to talk about things that can improve the class going forward. We'll see. One of the things I want to see is who shows up for the peer editing session, because I suspect that only a small percentage of the class are attending lecture, and I want to discuss why that is and what we might do about it. Okay, so some wrap-up remarks about ratio cut. So what is the obvious question to ask, given that we've just given an order log and approximation for ratio cut? Yes. Can you do better? Right? And the answer is twofold. We showed a so-called integrality gap of order log n for this linear program. We've shown that if you can achieve, if your LP has a certain ratio as its optimum, we can get within log n of that ratio. We only lose a factor log n from the linear program, okay? This gap is tight. Okay? You can prove that it is, for some graphs, impossible to do better, that you always have that log n gap between the value of the cut that you find and the value of the linear programming optimum. Okay? And the graphs that demonstrate this are expander graphs. Take a constant degree edge expander. What is an edge expander? Well, it is a graph such that for a cut S and S bar with the size of S less than the size of S bar, omega of S, it is, I have to precede this with, if we look at a degree D expander, okay, and then omega of D times the size of S edges cross the cut. Okay? Which, if you think about it, is what you would expect if the graph were random, right? If a vertex is picking some random collection of neighbors, right, and there's S vertices on one side and S bar vertices on the other side. S bar, not S. No, wait, S, right. So you've got a smaller side S. Each vertex on that smaller side is picking D neighbors, right? But basically, S bar is bigger, so each of those D neighbors has a 50-50 chance of being on the other side. So you'll have omega of D neighbors on the other side for each vertex, which means that you'll have D times size of S edges going to the other side. Yes? And so this is what you would expect of a random graph, but actually it took a long time to demonstrate that such graphs exist. Okay, so there's a theorem that such graphs exist. Yes?
Does the condition have to be true for all cuts?
Yes, that's exactly the point. This is true for all cuts simultaneously. And so a plain old, union bound doesn't look like it's going to work, right? But the proof is by the probabilistic method. It's not very hard, and I was thinking about showing it to you, but I really want to get to the last topic, so I'm just going to assert that these graphs, which look like random graphs or behave like random graphs ought to, do actually exist. And the proof is you generate a random graph and you show it's an expander. Okay? For this argument, you can just say take a random degree D graph, and it will have this property. Okay. Now, what this means is that the optimum ratio, right? If any cut has at least D times smaller side edges crossing out of the cut, right? The optimum ratio is going to be this omega of D times S divided by S times S bar, right? So the s's cancel, and s bar is about n over 2. So this is going to be d over n. That's the optimum ratio for one of these degree d expanders. Okay. But if I set all of the edge lengths to 1 over log n, okay, how many edges are there in this graph? Well, there's d per vertex, so there's about dn edges, right? So then the total edge length is order dn times 1 over log n, or order dn over log n. But here's the really critical thing about expanders. Most vertices, think about how you reach other vertices. Think about the short, right? The constraint for our linear program is that the sum of distances between vertices needs to be large, right? And we've set a very small edge length here, but I'm going to argue that most vertices are separated by long paths, that you have to use a lot of these edges, right? And the argument is very straightforward. This is a degree d expander, so if I start at a particular vertex, I know that I can only reach d vertices in 1 hop. I know I can only reach d squared vertices in 2 hops, d cubed vertices in 3 hops, right? So most vertices are log base d of n hops away. From a given vertex, because you can only reach d to the k with k hops. It's actually d minus 1 to the k, but same difference. Okay. So most distances are larger than 1. And so this creates a log n gap between the value of the linear program and the sum of and the optimum value of the ratio cut. Okay. Let me put that in slightly more detailed terms. So what we have is that the sum of distances is omega of n squared, because we have n squared pairs and most of them are a distance 1 apart, right? But the sum of the edge lengths is order n log n, n over log n, n over log n, right? Not n log n, right? So the ratio of these quantities is order 1 over n log n. So there's a cut with ratio order. Sorry, yes, go ahead.
So for the most distances that are greater than or equal to 1, shouldn't it be like 1 over log d?
Yeah, there's a log d, but d here is a constant, right? It's actually 3. You can have degree 3 and you have an expander. Okay, random degree 2 graphs are not expanders because they tend to just look like cycles and trees, but degree 3 graphs are expanders. So yeah, think of d as a constant here. So this gives us a bad ratio, but a bad gap, right? Cut value is d over n, which is 1 over n, and the LP ratio is 1 over n log n. So that gap of log n is just fundamental to this linear program. So you can't do better by rounding this linear program. You're always going to have to worry about losing a log n factor. Okay? But that just means that this linear program is not good. Right? There are better algorithms. which are based on a weird idea called expander flows, which are a weird chimera of flow and expanders, where you're trying to sort of fill up all of the cuts of the graph in a weird way. And the current best approximation ratio is root log n using these expander flows. So a significant improvement on log n, but there's a lot of room to potentially do better, and we don't have any hardness results for a sparsest cut. So, if any of you are still thinking about a project, an order 1 approximation for sparsest cut would definitely earn an A. Okay, so you can keep that in mind. I should also add, we were looking at sort of all pairs. There is a generalization to log k if you're only worried about separating k-specific vertices of the graph. When you talk about the number of pairs of these special vertices that are cut instead of the number of vertices of the entire graph that are separated. There's tons of really beautiful work on metric embeddings. I've only scratched the surface here. Another really amazing application is Fiat Bartal. A group of people showed that you can embed any metric into a convex combination of tree metrics. A tree metric is pretty much what you would expect. You make a tree on the nodes, and the distance is just the distance between the nodes in the tree. Okay? And that has really powerful applications in online algorithms. If any of you took my advanced algorithms class last year, or will be taking it next year, online algorithms are algorithms where you get the input a little bit at a time and you have to respond to that input as it arrives. And you're trying to do well against, compared to an adversary who knows what the whole input is going to be. One of the canonical problems in online algorithms is known as the K-server problem, which is basically about sending taxis to pick people up and minimizing the total distance that those taxis need to travel. And the K-server problem was defined in the 1980s, and the first breakthroughs gave exponential competitive ratios compared to this prophetic adversary. But the tree embedding techniques give you a log k approximation ratio, or competitive ratio for the K-server problem, which the best deterministic algorithms can only do about a factor of k. So it's an exponential improvement using randomization, which is based on this embedding idea. Okay, so lots of other beautiful applications. All right, in the last few minutes, well, no, maybe I won't tell you. Maybe I won't. No, I'll save this for next time. On Friday, I'm going to introduce the final topic, which is Markov chains, and I'll lecture on that on Friday and Monday. I'm going to put a little bit of homework about Markov chains onto the PSET, just because it's fun. Markov chains are a model of sort of the evolving state of a system. And what makes them interesting is that the model says that the system evolves in a series of steps, and at each step, the state of the system is random but dependent on the previous step. Okay. What's important is that it's not dependent on any of the earlier steps. So you can locally advance a Markov chain. You look at the current state, you flip some coins, and that tells you the next state. And this is a beautiful model for a lot of what goes on in the world, right? A lot of what goes on in the world is memoryless. What is the situation now matters for what's going to happen next, but what came before, how you got to now, doesn't really matter. And modeling that mathematically opens up all sorts of really interesting applications and questions, and we will look at those on Friday and on Monday. Yes?
The schedule says there would be 4 lectures on Markov chains, but if we don't have a lecture today and we don't have one next Wednesday, it will only be
That's right. I mean, we're squeezed for time, right? So we'll do a lecture on Friday and Monday, and if people want to see more, I can give some optional lectures, later to fill in the gaps. I'll poll to see if people are still interested in hearing from me yet again, or whether you want to just focus on your projects after Thanksgiving. Okay? Great. I will see you on Friday.